Hey class, Professor Larrick here for MET 110, our violent atmosphere. This first video is going to present a brief introduction to the atmosphere. Specifically, let's talk about the atmosphere's composition, its various layers, as well as the properties of the atmosphere that we use to describe its nature. Now, the first thing to note about the atmosphere is that it is extremely thin compared to the Earth itself. Now, this video text is a little bit overdramatic, but you can see it really nicely. The Earth's diameter is 8,000 miles, whereas the atmosphere is only 60 miles deep. And this thin blue haze that you see here, that thin blanket of gas, that's our atmosphere. But don't be fooled by its small size. The atmosphere is why we exist as a human race. It supplies the oxygen that we need to breathe, and it protects us from harmful rays from the sun. There's trillions of air molecules that make up the atmosphere, and 90% of them lie within the lowest 7.5 miles. Now when we zoom in, we can see 4 primary layers to the atmosphere, as well as the boundaries that separate them from each other. Now the root sphere corresponds to layer, while pause corresponds to level. So we have the troposphere, the stratosphere, mesosphere, and then the thermosphere. And between them we have the tropopause, stratopause, and mesopause. Now let's just focus in on the lowest two, because those are the ones that are going to be most impactful to the human race. So when it comes to the lowest layer, we have the troposphere. That contains the Earth's surface, that's where we live, and what we notice here is that on average, the temperature in the troposphere decreases pretty continuously with height. This is where nearly all clouds form and where all of our important weather happens. And the upper boundary of the troposphere is the tropopause, which plays a very important role in how tall thunderstorms can grow. Now the layer above that is the stratosphere. That contains the ozone layer. And because of that, it absorbs a lot of solar radiation, and you notice here that temperature evens out in the lowest part of the stratosphere, and then temperature actually increases pretty continuously with height. The composition of the atmosphere is quite complex because there's a lot of different gases that make up the atmosphere, and this table does a nice job showing that in terms of their names, symbols, as well as their fractional contribution to the atmosphere in percent by volume. But if we really break it down, there's 2 main ones. The atmosphere on average is 78% nitrogen and 21% oxygen. The rest of the gases make up only a small percentage of the atmosphere's volume, and these are called trace gases, and sometimes their amounts will vary depending on where we are around the world or in altitude. And the most important ones are water vapor and carbon dioxide. Water vapor can vary just above 0% to all the way up to 4%, while carbon dioxide makes up a very small fraction of only 0.037%. But they're still very important to how the atmosphere functions. Now, water is very unique in that it's the only substance in our atmosphere that can be found naturally in all 3 phases: gas, liquid, and solid. The generic term water is when we talk about H2O in liquid form. When it's a solid, we call it ice, and then the term water vapor is used to describe it in gas form. And both water vapor and carbon dioxide are greenhouse gases. Such gases are extremely important to keeping the Earth's surface warm enough for us to survive, because they let solar radiation pass all the way through, but then the energy that the Earth emits itself, these gases will actually absorb a lot of that and then give it back to the Earth's surface. So the greenhouse gases allow the Earth's surface and where we live to be warmer and livable compared to if they weren't there. Another important gas in the atmosphere is ozone. But ozone behaves like a double-edged sword, because naturally it wants to be up in the stratosphere where it's actually good for life on Earth, because it protects us from harmful rays from the sun. But when it gets to the surface, ozone is the main ingredient of photochemical smog. It can devastate crops, cause cancer. Ozone is bad when it gets to the surface. There's also a lot of particulate matter in the lower atmosphere that we call aerosols. They're microscopic in size, and they're put up by various surface processes. Breaking waves over the ocean can create sea spray and put up sea salt particles into the air. Strong winds over desert regions can loft a lot of dust into the lower atmosphere. Volcanic eruptions put up a lot of nitrates and sulfate particles. And then wildfires put up a lot of particulate matter. And all of these aerosol particles are important to clouds and various precipitation processes, as well as radiative balance and how solar radiation and energy from the Earth itself travel through the atmosphere. There's a subset of aerosols that we call pollutants, and these are aerosol particles that are put up into the air by various human activities and industrial processes. These aerosols can form acid rain, which we know can be very dangerous at the surface. It wears away limestone and other types of rock. It can destroy vegetation, such as entire forests that experience acid rain events. And when acid rain falls into water resources, it can destroy various wildlife populations in those areas. Clearly, the atmosphere is extremely complex, but as scientists, if we're going to hope to understand and predict and mitigate the various extreme and hazardous weather events that occur around the world, we need a way to describe the physical nature and evolution of the atmosphere. So to do that, we use its physical properties: temperature, pressure, wind speed and direction, as well as various moisture quantities, like relative humidity. Now, I'm sure you've heard most of those before, but we're going to cover them in more detail, and we're going to use them throughout the course of the semester to learn all about hazardous weather events. But that's all for now. Until next time,